Hello, everyone. Hi there. I'm Doug Picklick, editor of HPAC Magazine, and this is 30 Mechanical Minutes, virtual content for real-time professionals. Today, I'm having a conversation with a true expert in the hydronics field and someone I'm proud to say has been a regular contributor to HPAC Magazine for a very long time, Mr. John Siegenthaler. John, how are you doing?
Doing good, Doug. Glad to be
Awesome.
here.
Thank you for being here today. Today, we're going to be talking about optimal in-slab piping depth and the effects on heat transfer. Now, for many of you, or any of you who missed our last 30 Mechanical Minutes, John and I spoke about staple-up floor heating systems and the effectiveness of heat transfer plates. And you can see that exchange by visiting our YouTube channel or visiting hpacmag.com and searching under our Tech Pulse section. Before we get any further, I'd like to thank our sponsor for this episode of 30 Mechanical Minutes, and that is Arctic Heat Pumps. Thank you very much for your support. All right, John, well, this is it. We're talking about burying tubes in concrete. We see it all the time. So I'm going to ask you to tell us, how much is thermal performance affected by the tubing depth in a concrete slab?
Okay, let's get into it. Well, you can see a nice graphic here. It's easy to show the tubing in the middle of the concrete up here at the top. But in reality, there's been quite a few pours. I've witnessed pours where the tubing ends up being at the bottom of either a 4-inch concrete slab or even a 6-inch concrete slab. And as Doug mentioned, does it make a difference? And the answer is yes, it does make a difference. And I would tell you it's an important difference, especially if you're working with modern low temperature heat sources like air to water heat pumps, geothermal heat pumps, or modulating condensing boilers. So over here on the lower left, you can see a photo here. And actually, this is a good photo. This shows a lifting hook. You can see that. Mason has got that hook around that steel mesh, and they're actually lifting the tubing in the mesh as the concrete's being placed. So let me move on here. So again, I've kind of answered this already. I do want to stress that obviously when you pour concrete over tubing, you only get one shot to do it right. It's irreversible. So if it's an insignificant issue, don't worry about it. But as I've said already, it is a significant issue. And I want to show you why that's true. So here's a photo. This is a job. Actually, we designed this project and it was done about 30 years ago. And you can see the masons are placing a 6-inch slab here. And you can see that they are not lifting the tubing or the mesh. There's no provision to get that up off of that styrofoam insulation. And that obviously is going to affect the performance of it. And basically it makes sense. The more concrete that you have over the top of the tubing, the more resistance there is to heat transfer from the tubes up to the surface of that slab. And it also makes a difference on projects where you're using these knobby foam panels. And we're going to talk about those specifically near the end. But here again, you can see the tubing has been snapped into the foam knobs, and that looks to be at least a 6-inch slab that's going down. And when that's done, assuming they continue to place the concrete as they're showing it, the tubing is going to be at the bottom of the slab. So
I guess now you're going to tell us how mechanical contractors can best prepare the layout for optimal performance here.
Absolutely. We've tried several different things over the years, and quite honestly, the one that I feel works the best is to lift the welded wire fabric, or what most people call mesh, is to lift the mesh and the tubing during the pour, as you see in this photograph here. We've tried where we've put down concrete bricks, and the problem with that is this is only 10 gauge wire typically. And it bends easily. So if we have this wire supported on bricks like every 2 feet, as the masons walk on it, they're going to basically bend it down. and it is very difficult to walk on it without tripping. So it becomes impractical to try to do it that way. Now, if you're using steel rebar in the slab, that's different. The steel rebar is strong enough that you can walk on it when it's supported on what are typically called chairs, little plastic pedestals that hold the rebar up. That's fine, but welded wire fabric just isn't strong enough to let people walk around on it as they're placing the concrete. So rather than attempt that, leave the mesh and the tubing that's tied to the mesh on the foam, and make sure somebody, at least one person, their sole responsibility during that pour should be to lift that mesh. If it's a big slab, you might want to have a couple people involved. What you don't want to have happen is have somebody just toss the lift hook down and go grab a shovel or do something else as that concrete's coming out the chute or down the hose. You've got to stay, you basically got to stay right on the leading edge of the concrete as it's being placed and make sure you're lifting that mesh up. Now, one of the questions that comes up, well, what about when I go to do a saw cut in the slab for a control joint? Well, the detail we've used for years is shown here. Basically, you do leave the tubing at the bottom of the slab under the control joint location. You sleeve it 10 inches, 12 inches with a nice thin wall polyethylene sleeve. And that way, when you do the saw cut, which is typically only about 20% of the thickness of the slab, the bottom of that saw cut is well above where the tubing is. So mark out those control joint locations. We use spray paint and get the tubing fixed in place with that sleeve on it. And basically you just don't lift it at those locations. Okay. Now, years ago, these questions came up about the effect of the tubing depth of the slab. So we turned to a computer simulation, and this is something called finite element analysis, FEA. And what we do is we break the slab up mathematically into many, many hundreds of little pieces. And there are equations generated for each of these little pieces. And those equations are all solved by the computer. And it gives us a picture of what's going on thermally inside the slab. And the only thing we did in this simulation is to vary the height of the tubing. So over here on the right, you can see I've shown a tube in the middle of the slab, and we're going to take that up near the upper part of the slab. We're going to put it right down on the bottom. This is a 4-inch slab that we're looking at. And I'm assuming we've got a 3/8 hardwood floor, finished floor, that's bonded down with a mastic to the top of that slab. Now,
Can I just ask, John?
Yes.
Can I just ask, would it make much a difference if the finished flooring surface was tile or different?
It will make some difference in terms of how the heat spreads out laterally versus vertically. As you'll see, the wood is going to tend to enhance the lateral spread of the heat. If it was a very high conductivity flooring like ceramic tile or just a bare slab, you don't get quite as good a lateral dispersion, but you do get better vertical. And that's why we actually need a computer to simulate it. It's way beyond any kind of hand calculation that you could do. So this is what the computer generates. And you'll see these contour lines around the tube. And these are called isotherms. And basically each isotherm, each contour line represents a temperature. The higher temperatures near the tube, and as you move out away from the tube, progressively lower temperatures. And the red arrows that you see here, this is the direction of heat transfer. Heat always moves perpendicular to the isotherms. So this is really an incredible tool because it allows us to mathematically simulate what's going to happen. And as I mentioned, without tools like this, it would be almost impossible to come up with any kind of theoretical model of how this heat transfer to the surface of the floor is going to be affected by tubing depth. Okay. Now, here's another result from the FEA model. This shows a tube fairly close to the top of the slab. You can see it here. It's actually right at the top of the slab. Remember, there's a 3/8 wood floor over the top. And this red curve you see here, this shows you how the surface temperature would vary. And as you'd expect, it would be highest right over the tube. and then it falls off symmetrically in both directions. But you can see a pretty pronounced peak there. Okay. Now, the next slide will transition the tube down by about 1 inch, and you can see there's still a peak right over the top of the tube, but the peak is a little more subtle. You know, instead of the Matterhorn, it's some mountain with a little less of a jagged peak on it. But I also want you to notice that we're going downward in terms of the peak. And let's transition into the middle of the slab. And you can kind of see what's happening here. We're getting better lateral heat dispersion as we go down deeper in the slab, and that's beneficial. The ideal radiant floor would have a uniform temperature over its entire surface. We can only approximate that based on putting tubing into the slab, and of course, the closer the tubes are, the better the approximation is. And quite honestly, it's fine in the sense that very few people will ever complain that there's a 1 or 2 degree difference in the surface temperature of the floor. It's basically indetectable. Now, if we take the tube right to the bottom of the slab, we're getting pretty good lateral heat dispersion, but because the peak of this curve is so much lower, our surface temperatures are lower. It's more uniform, but it's lower surface temperature, and ultimately that reduces the output from the floor. So as we go deeper, we're going to get less output for the same tube spacing and the same water temperature. By the way, these are all based on 100-degree water in the tube and a 70-degree room temperature, and they all assume a 1 inch of polystyrene insulation under the slab. Again, any specific construction, if we vary the floor coverings, if we vary the amount of under slab insulation, if we vary the tube spacing, we would reconstruct another FEA model and run a simulation. Okay, so these are snapshots. This is just a quick comparison. Starting with the red curve there, again, higher surface temperatures, but a much stronger, what we call temperature gradient, a much more noticeable variation in floor surface temperature. And as we take the tube down deeper, we get lower surface temperatures, but again, more uniform temperatures.
So with the different heights, the water temperature can be adjusted to make the difference?
It can. And I got a slide coming up that'll actually show that, Doug. The bottom line is, if you leave the tube at the bottom of the slab, you're going to have to go to higher water temperature to get the same output. And going to higher water temperature with a modern heat source like a heat pump is going to penalize the performance of that heat pump. So if you're looking to bring radiant floor heating and a slab type radiant distribution system together with a heat pump, it's important that you control this tube height, and ideally in the middle of the slab. Obviously, when you're lifting the tube and the mesh during the pour, you're not going to get it perfect. It's going to vary a little bit, but it's definitely better to lift that mesh and that tube, get it approximately near the center of the thickness of the slab, as compared to simply dropping the concrete on it and leaving it at the bottom. Now, these graphics just show, you can see what's going on here. We're moving the tube downward in the slab. And then the graph over here, we're not varying the water temperature. We're not varying the floor covering. We're not varying the tube spacing. The only thing we're varying is the height of the tube in the slab. And you can see as we go deeper, here's the depth of the center of the tube. You can see our output in BTUs per hour per square foot of floor drops. And I would say it drops significantly. We're going from, just below the finished floor at about 25 BTUs per square foot per hour. We're dropping down to maybe around 18. That's a pretty significant drop. Okay. So I guess one of the things I would tell you as a takeaway, don't let somebody tell you it doesn't make a difference where the tube is in the slab. Okay, it does make a difference, and it's especially relevant today as we move towards heat pumps and high performance condensing boilers as our increasing market share for the hydronic heat source. Now, how much of a difference does it make? Well, I analyzed a couple cases here. Here's a case of a house. This might be a typical 1980s, 1990s house. with insulation of that era, it might have a design load that requires the floor to deliver about 30 BTUs per hour for each square foot of floor. Well, if the tube is at half the slab depth, we're going to need about 120-degree water in the tube to do that. But if we leave the tube at the bottom of the 4-inch slab, we're going to go up to 134-degree water temperature to compensate for that extra depth or that extra amount of concrete over the top of the tube. That's a 14-degree rise in temperature. Now, in the days of non-condensing type boilers, we could just turn up our mixing controllers. It wasn't a problem to push this water temperature up. It didn't really have a lot of effect on the efficiency. But today, a 14-degree increase in water temperature is going to have a significant effect on seasonal efficiency, especially with heat pumps. Now, I cut that in half for a modern energy efficient house that would have a design load of about 15 BTUs per hour per square foot. So we're down, if we can keep the slab, or I'm sorry, keep the tube about halfway up in the slab, we need 95-degree average water temperature. But if we drop it to the bottom of the slab, we've got to go to 102-degree water temperature. So that's a 7-degree increase. You might say, well, that's not much, but if you start looking at coefficient of performance curves on heat pumps, you'll see that definitely does impose a penalty. And remember, it's a lifelong penalty. You're never going to be able to change the tubing in that slab. It's every year that heat pump operates, it's going to be partially impaired by the fact that you left the tube at the bottom of the slab.
Now, John, you had mentioned that Knobby, here we go, the Knobby foam panels.
Yep.
And what difference these or other new prefabricated solutions might be producing today.
Yep. And, there's a lot of product out like this today. And I want to just give you a little history on this. I actually remember seeing these panels in the European market, and this is going way back into, I want to say about 1980. So these products have been around for quite a while, not necessarily in the North American market, but they've been used in the European market, and the Europeans do things differently. The Europeans commonly will pour a structural slab in a building, then they will put the Knobby panels over the structural slab, not in it, but literally sitting on top of it. They put the tubing in, as you see here, and then they pour only about 8 to 10 centimeters. So that's roughly 2 to 2.5 inches of what they call screed, which is just it's a special concrete formulation with small stone in it that easily screeds out and trowels out over that. But I want to stress, they're only putting what we would call a thin slab over the top of these panels. They are not using these panels under 4-inch, 6-inch, or 8-inch thick concrete slabs. And one of the things that these panels were designed to do, and they still will work, when there's a thin slab poured over these panels, as concrete cures, there's tensile stresses that build up in it. It tends to want to shrink a little bit. Well, the traditional way to deal with that is to cut control joints, which basically relieve that tensile stress in the concrete so that you don't get arbitrary cracks in the concrete. But with a thin slab poured over the Knobby panels, if you look at the diagonals between these knobs, that's actually the shorter paths. And what will happen is the concrete will form what are called micro cracks or micro fissures. These are almost so small you can't see them, but over the entire floor area, hundreds or thousands of these micro fractures in a concrete will relieve that tensile stress without causing arbitrary cracking or without having to create sawn control joints. That's a really nice feature. So it allows the concrete to cure properly, relieve the tensile stress, but no saw cuts. That is not going to happen if you pour a 4-inch or 6-inch slab. There's simply not enough influence of these foam knobs to allow those microfractures to occur. So basically, we have a product from the European market that was designed for a specific way of installation, be placed over a structural slab and have a thin slab poured over it. And we are applying it differently. Now, there's nothing wrong with the R value of the product. And I certainly don't argue that, you know, the tubing will stay in place. There's a lot of nice features. I do have one thing, and I've asked manufacturers this, and I'll throw it out there again. As a designer, I need to make calculations on water temperature versus heat output. I need to know if the tube is at the bottom of a slab with these knobby panels as the slab's underside insulation. I need to know how that's going to perform. It's not the same as simply putting the tubes over a flat sheet of styrofoam. And the reason for that is you've got contact between the tube and these knobs on the side. Any place that that tube touches foam is a place where there is no concrete. And that does affect heat diffusion by conduction away from that tube. So in theory, you'd have slightly less output using a knobby foam panel than you would using the same thickness of the same insulation material and simply laying the tube flat on it. I don't think the difference is a lot, but as a designer, I look for information that allows me to not guess at that, but to make a calculation and know what kind of output I'm going to get. You know, if I find in that calculation my water temperature only goes up 1 or 2 degrees, I'm probably going to be fine. I don't consider that, you know, an issue. If I found it went up 5 or 6 or more degrees, I might say, well, you know, we've got to be careful here. We've got to make sure we aren't inadvertently penalizing the performance of that heat pump by taking a knobby foam product like this and putting a thick slab over the top of it. Okay, so again, there's less contact area between the tube and the concrete when we use a knobby product like this. And as I say, it reduces conduction. Remember, all the heat that comes to the surface of that slab has to come out of that tube and ultimately has to go through the concrete. So the more contact area there is between the concrete and the tube, the more efficient that process is going to be. So I kind of finish here. Unfortunately, I have asked manufacturers if they would consider doing or, you know, perhaps outsourcing some type of analysis that would give us accurate sizing models on this. You know, I guess I want to stress I'm not against the use of these products at all. I think they're excellent products. They serve a purpose, but when they are applied in a different method from what they were originally designed for, and this photo definitely shows that different method where the entire thickness of the slab is above the tube, I simply ask, tell me how it's going to perform so that my calculations and my designs are not, you know, based on crossing my fingers. It's based on knowing how this product is and how it's applied, how they're going to perform. So, Doug, I don't know if we have questions we want to get into, or if you have anything else to touch on.
No, we definitely have some questions here. I mean, certainly that knobby, the polystyrene seems to make the installation go a lot easier. I've just seen contractors just stepping it down, right, and
Yep.
creating the loops as they go. It sure seems simple.
It does. It's, you know, contractors like it for that reason.
Yeah, understood. Okay, we did have a question that came in. Someone asking if you could touch a little bit about slab sensors with regards to the location or the depth, even the type of slab sensors. Any input on that?
Actually, we've never used a slab sensor, and I'll tell you why. And actually, the question bears it right out. Where does the sensor go? Does it go halfway between the tubes? Does it go near the top of the slab, near the bottom, et cetera? And that's going to affect what it feels in that slab. For example, if the sensor was buried halfway between the tubes, it's not going to feel the heat moving through that slab as quickly as if it were perhaps right over the top or right next to a tube. To be very honest with you, I don't feel they're necessary. We've done hundreds of systems over the years, and we've worked with basically standard thermostats, and it's worked fine. So, you know, again, I'm not against the use of the product, but as an engineer, I look at it, tell me, you know, where does the controller that sensor wires to, where does it expect that sensor to be? And, you know, is the sensor in a well, you know, a piece of, for example, copper tubing with a cap at the end? And if so, is it got thermal grease on it? If it's loose inside a well, that is not a good, you know, that's not good, because any air gap around the sensor inside a well in any type of application is going to delay the response of that. So it's a good question. Honestly, I don't have an answer for it. Our experience has been that we've been able to do good performing systems without those slab sensors.
Okay, very good. You, in your example, I forget the under slab insulation you had, but someone asked, what about if the below slab insulation is increased to say 4 inches? Is that going to have an effect?
Yeah, it is. We'd have to model it with the FEA. It definitely is going to reduce the downward heat transfer. And I should mention too, you do have higher rates of downward heat transfer when the tube's at the bottom of the slab compared to approximately in the middle of the slab. I don't have a number answer for if we were to go with 4 inches of styrofoam. It's hard to say without doing the model.
Yeah. Okay. Adam asks if you have any experience with installing heated tubes for exposed concrete architectural slabs. Adam's concern is about the tubes promoting cracking, especially if they're not overlaid with reinforcement, I guess. Any special construction recommendations to mitigate this?
Any slab on grade should have some steel reinforcing in it. Typically on light slabs in residential, light commercial, it's usually a welded wire fabric, 10 gauge or possibly a 6 gauge wire. Some architects will want to go with, say, 1/2 inch rebar every 12 inches in both directions. So any slab should have proper tensile reinforcing. So it's going to be steel reinforcing in the slab. And typically there's going to be sawn control joint specified. And the control joints, yeah, again, in a 4-inch slab, control joints typically every maybe 8 to 10 feet. And what that is doing, what a control joint is doing, it's basically forcing the slab to crack at the saw cut, as opposed to waiting until that tensile stress builds up to the point where the slab finds its own crack path. So, you know, regardless of what kind of finish is on the slab, that steel reinforcing and control joint detailing really is important part of getting a slab that is stable. And I should mention too, just good practice, you know, you've got to have a properly tamped, properly stabilized subgrade. If you're filling, you know, like under a garage or anywhere, you're putting 3 or 4 feet of sand or some other kind of fill in there, you should tamp that down in lifts, make sure it's stable, put some water on it. You know, the radiant tubing, I have not found that radiant tubing in a slab as the cause of cracks in a slab. It's usually some other type of structural detailing that has been either omitted or marginalized.
Right. One of our attendees asked, you referred to the knobby polystyrene in the European method being placed on top of a existing slab. So this person's asking, can this European method be used in a garage slab? Would the insulation be strong enough not to flex and break up the floor surface?
Well, I'm assuming what he means by that is putting the knobby panels right on like the tamped subgrade, and then putting up maybe a 2 or 2.5 inch slab over the top of it. I would be hesitant to do that. you really, a thin slab is not going to be strong enough, especially in a garage where you've got some vehicle traffic. You could pour another slab, a sub slab, and there are some what are called flowable fill materials today. They're basically a high slump, lower strength concrete material without aggregate in it. And instead of putting sand or gravel and tamping it down, you can put these flowable fills in. Depending on what the strength rating of the flowable fill is, that might be an acceptable substrate under the knobby panels with, possibly a 2.5-inch slab over the top of it. What I would suggest there would be to go to one of the panel manufacturers and ask them specifically. There is one, I won't mention names, I'll just mention it is a European manufacturer that sells in North America that actually has done a very good job of showing different types of installation details. I do think it would help some of the other manufacturers that put these products out on the market to invest in creating more technical details on how these products can be applied. It simply builds confidence on the part of engineers or designers that are being asked to specify the products. They need to know, that question is a great example. Can I put this down on a tamp subgrade and do a 2.5-inch slab in a garage?
Yeah.
My gut tells me I would be very careful about it. But, I don't want to say that is the final answer either.
Understood. Okay, we've got a few more. Let's get to these. For the knobby panels, this is popular.
Mm-hmm.
If the concrete is 10 centimeters, so just a hair under 4 inches, is there still no need for control joints?
Well, 10 centimeters, about 2.5 inches, I believe. Or
2.5 centimeters per inch.
Oh, wait a minute.
So it's about 4 inches, I think.
I may have mislabeled it. I should go back to inches.
Yeah.
No more than 2.5 inches. If you go over 2.5 inches, I don't think the microfractures are, assured in the project. Again, panel manufacturers could tell you more about that, but 2 to 2.5 inches. I apologize. I may have mislabeled the centimeters on there, but no more than 2.5 inches for getting those microfractures.
Okay. People are asking about who was that panel supplier that does provide some data. You did suggest, is it the European supplier?
Yeah, I don't know. Are we allowed to use specific manufacturers here? Or?
Well, they're asking.
They're asking. Yeah, it's Schluter Systems. Schluter. It's a German company. Many people know Schluter for ceramic tile detailing, but Schluter Systems makes a product. It's called Becotec, and it's actually, I believe that's what we're looking at in this photo here. And if you go online, you can find technical information on several different systems with different thicknesses, different tube sizes, and so forth. And they have done, in my opinion, they've done a good job of providing good technical information to know how this product should be applied.
Okay. Someone did ask if there has there not been any FEA simulation of the knobby panels?
I have not done that, but that is something that I'll simply say that there are resources available to manufacturers. Even if the manufacturer doesn't have the ability to do that, there are companies that specialize in FEA modeling that could take drawings or a photo like this and create a model of a performance model. And the FEA software today is very advanced. Unfortunately, it's also very expensive and very long learning. It's a very specialized application. That's why you don't find contractors or even engineering firms that are designing radiant systems or hydronic systems. You don't find those engineering firms very often using FEA because it's a very specialized type of analysis and, as I say, pretty expensive software. but there are consultants that are basically experts and have this, and they could be hired to do this type of analysis.
Okay. Someone's asking, you mentioned our discussion about the sensors, suggesting that if you're not using a floor sensor, how do you keep the thermostat from being manipulated by the ambient temperature?
Well, the thermostat is going to sense variations in the room temperature. I mean, standard thermostats, you know, the practice of mounting them, you don't want a thermostat mounted where sunlight's going to shine on it. You don't want it over a heat source. We had a project once where we had a thermostat and the homeowner installed a little water cooler, just, you know, just a little tiny refrigeration device to keep water cool. And they put it right under the thermostat. And just the heat coming off that little water cooler was affecting the operation of the thermostat. So, you know, thermostat locations need to be thought out. You don't want any kind of sunlight or heat from other appliances affecting it. But typically with a radiant system, we'll look for a thermostat that has a nominal 1 degree differential. It can be a pretty tight differential. And if you're using outdoor reset control to control the water temperature in the floor, in my experience, those thermostats have worked just fine. We haven't used any what I'll call radiant specific thermostats. I know there are some products on the market that describe, they basically have a larger surface area that is supposed to better detect the room temperature, the radiant temperature of the room. And you know, again, I'm not opposed to those being used, but our experiences, I mean, we've done everything from the old T86 Honeywells up through something like Ecobee type or even a Nest thermostat. And we've, you know, we found the standard air sensing thermostats have worked fine in these applications. Okay.
We're going to have to cut it off soon, but let me just see here. This person mentions that their tubing is usually stapled to foam under the rebar, but they're also using 4 or more inches of insulation. So that's
well, again, that's a specific case where, you know, if you go back to the slide of how we put these FEA models together, you'd have to reconstruct it with thicker insulation. And, you know, that's actually why we use FEA, because, you know, we can only guess at what's going to happen until we simulate it and see what's going to happen. Again, I would tell you, even the slab that we're looking at, let's assume that's going to be a 6-inch thick slab with the tube right at the bottom. It's not as if that slab isn't going to properly heat that space. We're just going to have to use a higher water temperature to make that happen. And one other aspect of tubing at the bottom of the slab that isn't really nice is it significantly increases response time. So if you're doing things like temperature setback, or you know, you have a cold night followed by a sunny morning and you've got a lot of windows, sunlight coming in there, with the tubing at the bottom of the slab, it's going to take longer for that slab to actually stop releasing heat. And you'll tend to get into overshoots. So the response time of the slab is going in the wrong direction as you take the tube down to the bottom of the slab. So again, I've seen projects. We actually had a project once where we specified the tubing in the middle, and I got a call from an attorney. This was happened to be for a municipality, and the attorney said, the guys are out there, they're pouring the concrete, they're leaving the tubing at the bottom of the slab, and your plans say halfway up through. Should I go stop them? I said, well, half the slab was already poured. And the answer was, well, it's still going to work, but we're going to have to go to a higher water temperature. And that had an oil-fired boiler system with a mixing valve, so we could do it. I guess when you look at it holistically, and it's probably a good way to wrap it up, if you're building hydronic systems today and you're building around modern heat sources that operate at low water temperatures, operate better at low water temperatures, I would highly encourage you to get that tubing up off the bottom of the slab, get it up approximately in the middle of the slab. it is going to enhance the performance of that heat source for the entire life of the system. And quite honestly, you know, a slab like that in a building can last generations. We talk about PEX tubing lasting well over 100 years in low pressure, low temperature applications. So it's not something that should be trivialized, and it's not something that should be ignored.
Okay. And we're gonna close. I got just two things I'm gonna mention here. One person did ask about using, you know, the aluminum, kind of those heat transfer plates that we talked about last time on the staple up in a concrete slab, but I think you touched on that last time and not really recommended.
I'm not sure that would give you much of a benefit. And the other thing that might be a problem is the potential chemical reaction between the aluminum and the concrete. There might be a problem there. And I don't think the cost of doing that and the complexity of doing that would really return much. You'd be better off just tightening up your tube spacing a little bit. Maybe, you know, instead of 12 inches, if you went to 9-inch tube spacing, you would probably equal or exceed any performance gain from the plates.
And finally, is O2 barrier PEX a good pipe for radiant in floor?
Yes, it is.
Okay.
Absolutely. We go strictly with barrier pipe. There was a time in the industry where you know, there were opinions both ways. Do you use a barrier pipe or a non-barrier pipe? And I guess I look at it, a barrier pipe today is I call it cheap insurance. You do not want oxygen diffusion into your system. And going with standard plumbing PEX without a barrier is going to allow oxygen in the system. You might save a nickel a foot or whatever the pricing is. It's not worth it. Go with a barrier on all your radiant hydronic installations.
Okay. Okay, I think our time is up. We can't really accommodate any more questions. Thank you very much for everyone who has sent something in. If we didn't get to it, I will send something to John and perhaps we can get those questions answered for you personally. So with that, John, thank you again very much for participating in today's 30 Mechanical Minutes webinar. And yes, and thank you to Arctic Heat Pumps for sponsoring this edition of 30 Mechanical Minutes. And of course, thank you to everyone who joined us for this webinar today. A recording of this session will be available on our website, hpacmag.com, in the days ahead. And you can also see past episodes of 30 Mechanical Minutes under the Tech Pulse section of our website and also on our YouTube channel. So that's it. Until next time, thank you so much for joining us today.
Thanks, folks.
Bye for now.